So, welcome everybody, and let me introduce myself and our team. My name is Tamás Laboda, and I'm a structural designer at ESIKON Ltd. I have graduated at Budapest University of Technology and Economics at the Faculty of Civil Engineering as an MSc Structural Engineer in 2016. And since then, I'm working at ESIKON Ltd. First times as an assistant structural designer, and in the last 3 years as a design of the record and the partner of the company. I'm an impassioned user of FEM design. I have been the software during my university studies, and at our company we mainly use FEM design for the structural analysis since the beginning. Now we take part of some testing process too. For example, we have helped to develop the FEM design all-plan connection. Our company is a small, medium-sized Hungarian-owned structural designer team with 8 to 15 professional staff. Our story began approximately 20 years ago in the shadow of the castle of Eger, and now we have offices in Eger and Budapest too. We are proud of that our team consists of highly experienced professionals as well colleagues eager to learn and to develop. We mainly design concrete structures, monolithic reinforced structures, as well as precast concrete structures too. We do general structural design, from conceptual design through permit design to detailed design, and we also prepare shop floor drawings for the precast industry. We maintain strong relationship with precast concrete manufacturers, architectural designers, general contractors, and also software developers too, and we are very proud of that. Let me present you some of our projects designed with the help of FEM design. Our latest project is Andor Park. It's a residential building with 140 apartments over about 20,000 square meter net floor area. It is located in Budapest, District 11. The building forms 6 separate towers with ground floor and 5 upper levels, and a full area basement with parking function. The construction of the building is still in progress. The final deadline is in the third quarter of 2026. During the design, we used FEM design to efficiently design the structure with 3D global structural analysis and including seismic design. We also do some 2D part models to efficiently design the flat slab planes and the foundation slab, which is supported at some areas by piles. We calculated the reinforcement for the columns, the beams, and the shear walls, also with the help of the software. Our next project is Kasság Residence, which is one of a 3-part real estate development located also in Budapest. The residential building consists of 230 apartments with approximately 26,000 square meter net floor area. The building can be divided into 4 staircases with 5 to 8 levels and a full area ground floor with shops and garage, and 1 basement level with parking lots. During the design, we used FEM design for all the calculations here too. We have managed to solve a huge problem during the design of the structure. As you can see on the left side picture, it is the layout plan of the basement level. It has strict orthogonal column layout to have the parking function. On the right picture, you can see the plan view of the upper floors with residential functions. Here, the columns were located inside the separating walls of the apartments because, of course, nobody wants a column in the middle of the bedroom. So it is a varying column layout. As you can see in this section, the columns layout is very different on the basement levels and the upper levels, and it would be an impossible task for the architectural designers to align these columns. So we came with a solution, which is a thick load transfer slab, which is located above the ground floor, which is 70 centimeters thick reinforced concrete slab. The base idea was to make another foundation slab above the ground floor, so the varying layout columns from the upper side are supported with this slab, and the columns on the basement acts like strict layout piles. Budapest 1 office building is located also in Budapest. It's near the M7 highway in District 11. Our team delivered the structural design plans of the second and third stage of the building, and with its clover-shaped plan view and wavy facade, the building has an eye-catching appearance. The varying cantilever lengths of the flat slabs made the design process exciting. On top of the structural form, we had to solve a special foundation problem. One of Budapest subway tunnels will be located under the building. So as a solution, we have to design some reinforced concrete deep beams under the building on level P3 to protect the building, the future tunnel from the loads of the building system. That reinforced concrete box is named by the architects as the jewelry box. One of our bigger projects is Dürer Park Office Building 2, which is located in Budapest near the city park. At the end of the 19th century, a nunnery was built here. It was functioning as a school for disadvantaged students, and the nunnery has had its own chapel, not only for the students, but open for everyone. After the Second World War, Hungary became part of the Soviet Union, and religion has become undesirable. The Communist Party transformed the building, not respecting its past. And through time, the condition of the building has seriously damaged. Our project was to renovate the original building and integrate it to a new modern office building. As you can see in these finished pictures, the three-story original structure is highlighted with the white areas, and the new reinforced concrete structure with additional 3 levels got a back glass facade. On the right picture, you can see the renovated chapel, which is functioning now as an exhibition hall. On this plan view, you can see the existing building marked with the blue L-shaped area. As I have mentioned, it has 3 levels, the ground floor plus 2 upper levels. It has masonry walls, and the slabs were masonry wall slabs with steel I-section beams. You can see the cross-section of the slab above. On top of this old structure, we had to design 3 extra levels with regular reinforced concrete structure, columns, shear walls, and flat slabs. As an extension to the building, a new reinforced concrete structure was designed, marked with the green area. It has 2 basement levels, a ground floor, and 5 upper levels. During the design, we have to strengthen the existing slabs. We made it with topping concrete. Between the concrete and the I-section beams, we used Hilti shear connectors to maintain the shear forces. And the topping concrete not only ensures the compression zone for the beams, but also integrate them to a rigid diaphragm for the bracing system. The masonry walls didn't have so much extra capacity to support the additional 3 levels, so we had to design additional reinforced concrete columns integrated into the original masonry walls to support the superstructure. The columns are transferring all the loads from the upper levels to a new strengthened foundation. There's a common phrase often told by the architectural designers that from every building you can remove 1 column and the building remains stable. Now, we put that phrase into reality. We removed not only 1 but 2 columns from the ground floor. The building has originally an 8 times 8 meter column layout, but by the conference hall on the ground floor, 2 columns were in the wrong place. You can see it marked with red. So we remove them. How we do this? We designed here a special load transfer frame. On the first picture, you can see it during construction. During construction, we designed two steel columns to the missing points. The structure during construction remained 8 times 8 meter layout. All the columns were compressed elements during that time. On the top level, a massive deep beam were designed, marked with green on the top. And to help our task, the architectural designers asked a bigger opening in the middle of that. So after the structure was finished, we simply cut out the steel columns marked with red on the left-hand side. With that, the top deep beam started to transfer the loads from the middle to the sides for more compressed reinforced concrete columns. And the middle columns, marked with purple, became tensioned and tied up all the slabs to the top load-bearing structure. You can see some finished pictures of the building. On the left-hand side, you can see the inner garden. On the bottom one, you can see the basement of the chapel, which acts now as a canteen. And on the right-hand side, you can see the outside of the chapel. We all designed the elements using FEM design during the process. As I have mentioned at the beginning, we also designed precast reinforced concrete structures, buildings and elements too. The latest development is the use of precast concrete sandwich wall panels as facade for new buildings. I know in Scandinavian areas it's widely and commonly used, but in Hungary we are not so familiar with that structural form now. We have designed two office buildings located at Budapest area, which is the most developing parts of Hungary and Budapest. We have designed not only the reinforced concrete main structure, so the slabs, columns, beams, and the staircases, but we delivered shopwork drawings for the facade element too. The wall panels act not only vertical load-bearing elements, but are they part of the bracing system too. Some words about these panels. They have 7 centimeter thick outer shell with a special textured Recley surface. The walls have 20 centimeter load-bearing inner core. And between the concrete layers, 16 centimeter thick rock wall isolation can be found. The maximum dimensions of the elements is 5.4 times 3.8 meters. It's limited by road safety regulations. And the weight of the panels is 10 to 11 tons, which is limited by the tower crane capacity. The horizontal connection between the panels made with stirrups and on-site pouring to ensure the maximum shear force between the elements. And the vertical connections are made with roughened surface for stronger friction between the elements. Tension forces were handled with rebar couplers between the parts. Here are some pictures of the FEM design model. On the left-hand side, you can see that we used user-defined edge connections between the elements. And on the right-hand side, you can see we made the reinforcement with concealed bar elements. We also designed precast concrete buildings for the industry. One of our greatest projects was the Central European Logistics Center in Eger. The monumental construction included 8 buildings with 140,000 square meter net floor area. The longest building was the main corridor for the conveyor belt, which is 800 meters long. And the highest were the 2 high bay warehouses with 40 meters height. All the structures were designed with the help of FEM design, not only the 3-dimensional analysis and the seismic design for DCM category, but we checked the concrete elements itself and designed additional steel structures with the help of the finite element model. Our team delivered the structural design for a building for the new BMW plant in Debrecen. The building has a canteen function where 1,500 people can eat every day. We delivered the documentation with design and build process, so we had to do the works very quickly. Based on American samples, our company has developed a precast parking building system. In Hungary, 2 buildings have been already constructed with structural system. A ramp parking structure is made of double T-panels with 60 meters span. And the columns and the beams have earthquake-resistant connections, so no additional shear walls are necessary for this type of structure. We also design steel structures with the help of FEM design. On the left picture, you can see a swimming hole. It's in eastern Hungary, Kazincbarcika. The bracing system was made from steel structure, and the roof trusses with 42 meter span were designed with the help of FEM design. On the right picture, you can see a FEM model of a smaller boiler room for the energy industry. We choose the steel structure here because the soil here has a poor load-bearing capacity, and we had to reduce the dead loads. It was a pleasure and a fun task to design the fixing of the mechanical equipment and tubes inside this technical building too. Let me tell you some few words about how we use FEM design. As a structural designer, we had to build 2 models, a calculation model in FEM design, or FEM model, a FEM software, and a geometrical one at the CAD software. That doubles the work. So to speed up the process, we often communicate with the architectural designers in IFC format, which is exported from FEM design itself. During the design, we have to work with other structural designers like geotechnical engineers or precast concrete manufacturers. And with the help of SAF format, we can change data and share models between the different finite element softwares. During the design method, we can accelerate our workflow with IFC import. So if we get the geometrical data from the architecture engineers, we can import it to FEM design and speed up the model build process. And when we're done with the design, we can export the reinforcement to help to the Alplan connection. So the work is done mostly in FEM design, and we only have to add some details to the rebars in Alplan. We are always looking for the most efficient workflow. In the past, we prepared the reactions and internal forces completed in FEM design, but we summarized these reactions and internal forces and took it to another software. We do the detailed design in another software. From that separately, in another workflow, we made a 3D geometrical model in a CAD software with the reinforcement. So it is a lot of company standard process descriptions for the colleagues to learn what software, what data transfer from one to another software. Now we managed to shorten the design flow. We prepared the 3-dimensional global structural analysis in FEM design. We designed the main structures with that model. For example, the flat slabs, the beams, the columns are reinforced there. But now we use some other detailing softwares too, for example, for the footing design. With the help of the Allplan FEM design connection, we can export the reinforcement and add some detailings to the drawings there. That's where we are now. In the future, we would like to move further and calculate all the structures in FEM design or FEM design TrueSoft related software, for example, like Simplex. The reinforcement in our vision, the results came from the CAD software. And in the future, we don't need to build 2 different models. We will be able to do all the analysis and the detailed calculation in FEM design And thanks to automated connections, the CAD software will automatically prepare the drawings for us. That means automated workflow, zero data loss, maybe some AI-added design, and no repeated manual work, so we will have more time to design efficient and interesting structures. Thank you for your attention, and if you have any questions, feel free to ask me.